Okay. You'll notice there are blue areas. That's places where apparently the ocean is doing work on the moon. It's a little bit hard to tell if they think the Irish Sea is still one of those areas because of the jumble up there. But the main point of this is, first of all, the main point of Egbert and Ray is, first of all, it shows there is significant energy loss in the deep ocean. It's not all happening due to tidal bottom boundary layer friction in shallow seas. There is some mechanism operating here around Hawaii. Well, I'll read it. All areas of consistently enhanced dissipation have significant bathymetric roughness, generally with elongated features such as ridges and island chains oriented perpendicular to tidal flows. Okay? So that's the conclusion from Egbert and Ray, that there is a deep ocean energy loss mechanism to do with bathymetric roughness. Yes?
How do you separate out that contribution of zeta due to tides and not due to maybe waves or something?
Oh, well, what Egbert and Ray are doing, they have measurements of zeta from a satellite. They believe the Laplace tidal equations. They know the forcing function very accurately. So all they're doing is taking a model forced only by the only at the tidal frequencies. So everything in their model is tides by construction. Okay. For F, they pick different models, either a nonlinear drag law or a linear drag law. It's rather insensitive to those choices. I mean, there are interesting details which depend on how you model F, but in the end, no matter what you do, you see significant dissipation around the same places, which always coincide with island arcs and bottom roughness. Okay. So at one stage, people thought, well, maybe all of the tidal dissipation is just due to the turbulent bottom boundary layer in shallow seas. So Egbert and Ray are saying, no, there's something going on in the deep ocean, and here's a map of where it's occurring. And this is how I think Monk and Wunsch, or Wunsch and Ferrari, got one of the numbers in their diagram, their energy plumbing diagram. They got it from Egbert and Ray, which shows that there's about 1 terawatt of deep ocean tidal dissipation. And it's thought that what's going on here is scattering of the barotropic tide. The tide is independent of depth because the forcing is independent of depth, but when it goes over bumps on the bottom, it creates internal waves, and oceanographers call that process tidal conversion. And that's an important source of ocean internal wave energy and of tidal friction. So maybe I'll skip that. I'm not going to have time to talk in detail about the idealized models which have been developed in order to actually try to calculate the tidal conversion rate, but I'll give you an idea of the process. So what we have here, this is all linear theory, solving the linearized Boussinesq equations with specified buoyancy frequency, some function of z. We also specify a barotropic sloshing back and forth, just a uniform velocity, which models the tide with an EM2 frequency, say 12.4 hours. There's a bump on the bottom, the fluid is stratified, and as a result of that motion across the bottom, you radiate energy into the internal gravity wave field. Okay, so that's what Egbert and Ray have very plausibly seen in their data and in their reconstruction of the dissipation. It's scattering of the barotropic energy into the internal gravity wave, field.
And then they break or something like that?
Yes. Yeah, so it's thought, I was just asked if these waves break. Yeah, so this is a way of energizing the internal gravity wave field. Those waves propagate some unknown distance through the ocean, somehow dissipate by breaking and mixing. And so this is a way of both powering the internal gravity wave field and also creating mixing at sites which are distant from topography.
So is the mechanism of braking similar to what is seen in the atmosphere? You go and the density becomes lower and the amplitude just.
No, it's completely different. It's thought to be completely different from the atmospheric mechanism, which as I understand it involves the amplitude increasing because things propagate vertically. So what you might not see from this movie is this is a movie where the radiation is going upwards into a semi-infinite region, but of course the ocean has a lid only 4 kilometers up. And so if you really want to do this linear problem properly, you have to put the lid on. And then the problem is best thought of as radiation of principally mode 1, that is vertical mode 1, horizontally away from the generation site. So there's very little upwards propagation. What you see is more like something in this figure that I didn't have a chance to talk about, which is these are observations by Ray and Mitchum. This is Hawaii, the Hawaiian island chain, most of which is underwater. Notice the scale here, so this is 30 degrees of longitude. And these are internal gravity waves observed by satellite, which is measuring sea surface height, and they're very clearly propagating away from Hawaii in both directions into the deep ocean. And it's principally mode 1 and mode 2. A significant fraction of the semi-diurnal tide is phase locked to the astronomical potential and can modulate the amplitude of the surface tide by about 5 centimeters. And it's coherent for great distances, that is thousands of kilometers away from the generation site at Hawaii. Okay. And it's principally vertical mode 1 and vertical mode 2. So it's not, don't think of it as a vertical propagation problem, think of it as a horizontal propagation problem where these waves are now propagating away from this generation site. Yes, well, I think I'm finished. Okay, thank you.
No, we have time for plenty.
And these internal tides, they break eventually in the shallow sea, I guess, no?
It's a mystery.
It's a mystery? Because
Yeah.
if it's in the shallow sea, it's the same region when you have this tide, like this main tidal dissipation. So it's like reinforced.
No, well, our hope is that maybe they break someplace which is more interesting and create mixing somewhere else. The shallow seas are well supplied with mixing. They don't need any more.
Very simple. Can you remind us how the...
You have to use the microphone.
This is... Oh, hello? Hello? How soon after the moon was formed did the oceans appear? Or is,
Well,
I forgot.
first of all, the formation of the moon is controversial. I think the smart money today is on bolide impact, maybe 3.5 billion years ago. And I'm not sure what the state of the oceans were. I know that 2 billion years ago they were pretty much as they are today. That is, they covered 70% of the surface of the Earth. So I think you'll have to do a little bit of research to answer that question. I don't know in detail.
Hello.
Hello.
In the picture you showed the part that the energy was dissipated in the ocean, like in the middle of the ocean. There were patches. Is there any? Yeah, this one. Particular explanation why those regions have patches and there's nothing else elsewhere?
Yes, I'll read it. All areas of consistently enhanced dissipation, and here's one, a very reliable one, this is Hawaii, have significant bathymetric roughness. So that all places where there's mountains, island chains, and those are exactly the places where you'd expect to see this internal wave generation mechanism working most efficiently, because you've got this stratified fluid which is being carried back and forth over bumps, and that's a good recipe for generating internal waves. So keep in mind the tide itself is independent of depth, right? So it's a stratified fluid, and if the bottom was flat, you'd have this stratified fluid simply moving back and forth independent of depth, and the other number to keep in mind is the tidal excursion distance, which for instance would be a typical velocity divided by the frequency, is 35 kilometers. So it'd be an oscillation with meters. Yes, meters. Would be 35 meters, a very small distance. And so what's happening is, well, I think it's shown here. Even if the excursion distance is only 35 meters and the topography is, say, 100 kilometers in width, just the passage over that slope results in internal gravity wave radiation.
So Bill, just to make clear, so you had 3.2 terawatt. Now you get 1 terawatt of dissipation through this deep ocean mechanism.
Yes.
So the difference is in the shallow seas, or
Exactly. Yes.
and so I mean, is it clear why this method should not give also the number for the shallow sea?
Well, there's so much more going on in the shallow seas because for instance, I think the Irish Sea is, it's embarrassing. I don't know whether it's 67 feet or 67 fathoms deep. And the bottom boundary layer is such a potent way of creating turbulence from the tidal flow that, and also because of that, there's almost no stratification really in the Irish Sea, for instance. It's just mixed top to bottom by the strong turbulence. It's not that deep, so you're not going to generate internal gravity waves without any density stratification to work on. Yeah, so I think for all those reasons, in the shallow seas, it's simply topographic roughness once again, but turbulent drag.
Sorry, if shallow sea is more homogeneous, then it's gonna be less efficient to generate mixing than in the deep ocean. If it's all homogeneous. And
Yeah, it's already mixed. It's over-mixed. We don't need any more mixing there.
okay.
Yeah, so Raf is going to talk about maintenance of a Bissell stratification, which is all about why the deep ocean is stratified. Yeah, and the effect of internal gravity waves in doing that. Yes.
May you repeat?
Yes, so I'm being asked if the G.I. Taylor estimate is consistent with Egbert and Ray. Yeah, so Egbert and Ray, yes, and the shallow seas are more or less sitting ducks for an estimate like this because the tidal flows, I think, are pretty well known in most of the shallow seas. The main question of Egbert and Ray was anything else going on outside shallow seas? And the answer was yes, an unambiguous yes.
Okay, just the last question.
I don't think you can use Egbert and Ray to say anything about shallow seas because the altimeter has serious issues in measuring sea surface height close to coastline, so they
Yes,
don't
that's
even
true.
give you a number.
I'm actually not sure if they were using, yes, probably you're correct, but were they actually only using the satellite for their assimilation? They were, okay. Yeah, so this is, well, yeah, this is purely satellite data, so it's probably not even reliable in the Irish Sea, for instance.
Okay, we can thank Bill for his first lecture.